Next, we have Simon, who is telling us about destabilizing errors.
Hi, can you all hear me? Great. I'm Simon, and today I'm going to show you how we brought a key feature of the Viper verifier family, namely heap-dependent expression assertions, to Iris. And as we will see later in the talk, this required us to make some quite fundamental changes to Iris. This is joint work with Niklas, Haoyi, Michael, Andrea, Peter, and Derek. I want to start with a question. How do you reason about large stateful programs? The challenge here is that if you think about a larger program and you decompose it into its individual parts, then one part of the program, such as the function b up here, can modify the state, say store 41 in the location L, and a totally different part of the program, such as the function h down here, can observe these modifications. So everything is implicitly connected via the shared state, which makes reasoning about these programs more difficult. One popular answer to this question over the last 10, 20 years has been separation logic, because separation logic enables modular verification of stateful code. What that means is we can verify our code function by function, even if it involves pointers, references, and so on. And the key feature of separation logic that enables this is ownership reasoning. Assertions in separation not only describe the contents of memory, they also carry with them ownership that allows us to access or modify that memory. And we can see this quite clearly in the specification for the function b from the previous slide. It first of all tells us that we update L from an arbitrary value to 41, but it also tells us a little bit more. It tells us that b only accesses L and no other locations, because it only gets ownership for L in the precondition. And one separation logic that has been particularly popular over the last couple of years is the separation logic framework Iris, which you can use for all kinds of verification, including fine-grained concurrency verification, multi-language verification, and for developing semantic models of type systems, and much more. But, shocker, separation logic is not the only foundation for ownership reasoning, and Iris is not the only tool out there. Another quite powerful approach for ownership reasoning is implicit dynamic frames, which has been used quite successfully by the Viper verifier family, which includes Viper itself and also several frontends, such as Nagini for verifying Python code, Gopra for verifying Go code, and Prusty for verifying Rust code. And we can see the differences between these two approaches quite clearly if we put them side by side. In separation logic, we typically reason about resources, such as L points to V, which combine together ownership with knowledge about the contents of memory. In implicit dynamic frames, the foundation of Viper, these two are separate. We have access predicates to reason about ownership, and heap-dependent expression assertions to reason about the contents of memory using program expressions. And I want to focus on these heap-dependent expression assertions. They are somewhat of a strange animal if you have a separation logic perspective. They assert facts about the contents of memory without asserting ownership for that memory. And when I first saw this, I was a bit confused, I have to say. So I started wondering, well, why would you want heap-dependent expression assertions in the first place? And also, how do they work? And slightly differently, well, can we usefully integrate them into separation logic and into Iris in particular? I'm now going to first focus on the first question, and then in the rest of this talk, we will explore the second question. Now, to answer the first question, I've brought along a little example here. In this example, we have a produce buffer function that produces a buffer B, and then later on, we will call a read-only client that, as the name indicates, is supposed to not modify the buffer. So we compute the checksum of the buffer before and after the read-only client, and then we assert that they are the same at the very end. Now, you can verify this example in separation logic, and this is what it would look like. After we produce the buffer, we get a point to the buffer contents, as let's say a list of integers u. And then we compute the checksum. And we need to remember something about check1 now to do the rest of the verification. So what you would typically do in separation logic is define a mathematical version of the checksum function, CS here, that is then applied to the buffer contents. And we just remember that check1 is CS of u. We call read-only client, and then afterwards we compute checksum a second time, and we remember that check2 is CS of u. And then we can prove that the assert succeeds because check1 is CS of u and check2 is CS of u, so they both must be the same. But there's a little bit more to the story here. If we want to verify the entire program, we also have to verify checksum. And that involves providing the code for checksum, of course. But then we also have to define this mathematical function CS that operates on the buffer contents. And then there's also a proof obligation. We have to show that the code actually implements this function. Which means, in other words, we actually end up proving functional correctness of the checksum function. Now, if you think a bit about this example, then you might realize that that's a bit overkill. For this example to work, we only need that checksum behaves like a function. So it should be deterministic, it should terminate, it should modify the memory, but we don't really care about which algorithm checksum implements. In particular, there's a lot of redundancy between actually providing the code and then separately providing basically the same thing again as a mathematical function. It would be nice to avoid that. And that's where heap-dependent expression assertions come in. First of all, they are logic-level assertions, so we can use them in our specifications and we can use them in our proofs. And they're assertions about program expressions that themselves can access memory. So how does this help us in our proofs? Well, with heap-dependent expression assertions, checksum of b equals check1 is now a logic-level assertion that we can use in our proofs. So here's how the proof would change with heap-dependent expression assertions. We first get that points to for the buffer, and then instead of having this mathematical function, we just remember that checksum of b currently evaluates to check1. We call the read-only client, and afterwards we remember that checksum of b also evaluates to check2. And then the proof obligation in the end becomes that if checksum of b equals check1 and checksum of b equals check2, then check1 must be the same as check2, which is of course trivial in this case. So now, for the rest of this talk, let's turn to the second question. Can we actually usefully integrate these heap-dependent expression assertions into separation logic and into Iris in particular? And that's what we did in this work by introducing Daenerys, which brings heap-dependent expression assertions to Iris via a new form of resources, unstable resources that, as we will see in a second, violate the central frame rule in Iris, and a new modality, the frame modality, that now controls how framing works. And really, Daenerys consists of two parts. The first one is how we model heap-dependent expression assertions in Iris, and for that we have developed a version of Iris with unstable resources. And the second part is then how we reason about these heap-dependent expression assertions, and in particular how we connect them to SMT solvers. So let's start with the first one. Why is it even hard to bring heap-dependent expression assertions to Iris? I've already hinted at this a bit earlier. They assert facts about the contents of memory without asserting the corresponding ownership. And that is not something you should do in separation logic. So what they do is they violate the central frame rule of separation logic. In particular, Iris supports this very general form of the frame rule, which says if you have proven a Hall triple PEQ, then you can frame on any additional resource R, and it will be left unchanged. And this is a, if not the key principle in separation logic to achieve modularity, and used quite widely in Iris. But in the presence of heap-dependent expression assertions, this rule as it is written here is unsound. And to illustrate that, I've brought along a counterexample. Suppose we have a buffer initially storing 5 and 7, and now we update the first entry in the buffer to store 42. Typically, with the frame rule, we could frame anything around this, including, in the presence of heap-dependent expression assertions, the fact that checksum of b currently evaluates to check. But of course, if we change the contents of the buffer, then the checksum cannot stay the same. And that is actually quite a problem, because Iris bakes in framing at its very core. It is central to how resources in Iris work. And so what we did in this work is we redesigned framing from the ground up. So we started with the resource layer of Iris and added a new form of unstable resources. For the Iris experts in the room, what's going on here is that typically every update in Iris preserves all potential frames, and we changed that. We introduce a new update that discards part of the frame, the unstable part, and only preserves the stable part. On top of that, we have then defined a new points-to assertion that describes the contents of memory without asserting ownership, the unstable points-to, and that is erased on updates, and a new modality, the frame modality, that now controls how framing works. On top of that, we have defined one core heap-dependent expression assertion for evaluation, namely that E currently evaluates to the value V, and we have revised the frame rule to now include the frame modality. I want to linger on that last point for just a second and explain how framing now works in Daenerys. For existing resources, such as points-to that carries ownership, we can just put them inside of a frame modality, which means we can arbitrarily frame them. Heap-dependent expression assertions alone cannot be framed. As we saw earlier, that would be unsound. But what we can do is, if we have a heap-dependent expression assertion, together with enough ownership to stabilize it, to make sure that its value will not change, then we can frame the two together. Now next, let me say a few words about how we connect these heap-dependent expression assertions to SMT solvers and how we reason about them. Typically, there's quite a wide gap between the Iris world and the SMT world. In Iris, we reason about separation logic, and we do so mostly manually using the ROC proof assistant. SMT solvers, on the other hand, provide great automation, in particular for theories like big vectors and integers, but they reason about first-order logic. And heap-dependent expression assertions are one nice way to bridge this gap. More specifically, they allow us to use SMT solvers to automate parts of an Iris proof. Let me explain in a little bit more detail how this works. So at the top here, I've written a formula in first-order logic. And this is something that an SMT solver could understand. It says that if for every buffer B and unsigned integers, 64-bit integers C1 and C2, if the checksum of B equals C1 and the checksum of B equals C2, then C1 must be C2. This is basically the formula that we've been working with so far. Here's it written out as a heap-dependent expression assertion again, in full detail. And the point I want to make here is that they are very similar, but, as I will show you now, they're also subtly different, and that's where the work of this part went. In first-order logic, we have uninterpreted and interpreted sorts. In heap-dependent expression assertions, on the other hand, we have separation logic predicates with unstable resources. In first-order logic, reason about things like uninterpreted functions. In heap-dependent expression assertions, that is the program code itself. That's the whole point of having the program code at the assertion level. In first-order logic, we have first-order equality, two equate terms. In heap-dependent expression assertions, we reason about evaluation. More specifically, we want to evaluate our expressions. And then lastly, in first-order logic, we have implication. This is the classical implication of first-order logic, whereas in heap-dependent expression assertions, we have the implication of separation logic. And if you know the two, you might also know that they behave quite differently. So what we did in this work to bridge this gap is we proved the following key theorem. We established a connection between heap-dependent expression assertions H and first-order formulas pi, such that if pi holds in first-order logic, then we can assume H in Iris, where the connection is basically the one that I outlined on the previous slide. So for example, we would relate the code of checksum to the uninterpreted function checksum. And then the proof of this is beyond the scope of this talk. You can find the details there in the paper. But basically what we do is we construct a model of first-order logic based on heap-dependent expression assertions, where we define a logical relation that itself is a heap-dependent expression assertion to interpret first-order sorts. As I said, you can find the details of this in a paper. What you can also find in the paper is an evaluation with several case studies, including some that illustrate the strengths of heap-dependent expression assertions, some that leverage the connection to SMT, and in particular their bit vector theories, and some that go beyond what Iris and Viper can do individually. And Daenerys is fully mechanized in ROC and extending Iris. And with that, I thank you for your attention, and I'm happy to take any questions that you may have.
Hi, great talk. Matthew Parkinson, Microsoft. Could you talk a bit about non-determinism and if this works for non-determinism?
Good question. So we require the expressions themselves in the heap-dependent expression assertions to be deterministic. Because otherwise, for example, basically the implication that I showed you on the slide wouldn't hold. But the programming language itself doesn't have to be deterministic. That can have concurrency, as we actually do in the paper, and lots of other non-determinism if it wants. The crucial bit is that the expressions for that particular notion of evaluation that we've chosen are deterministic.
Hello, really enjoyed the talk as well. Can you talk about how the frame modality relates to the previous formalization of implicit dynamic frames?
Yes.
My understanding is, of the former, is that you just make sure that every expression in the logic is well framed. So I wonder if there's a relationship there.
Yes. So basically, I tried to write this down in a separation logic style to match the rest of the talk. But what you usually do in implicit dynamic frames is you separately, outside of the logic, assert that the proposition is self-framing, the one that you want to frame. And what we do in Daenerys, one way to think about it, is we internalize that notion into a modality that you can then have in a logic and pass around.
Thank you.
Hi. Really cool work.
Thanks.
So, I mean, I'm sure you're aware there's this other work about the next-gen modality, which also introduces a feature which breaks framing and also solves it by introducing a new modality. Have you thought at all about the similarity between these, if they're, one encompasses the other, or even if they're compatible?
Yes. So the next-gen modality, as far as I understand it, basically applies a function to the resource that says, okay, this is how the resource should change. And so instances of their modality that they show are persistency and plainly, for example. We want something different in that we want to preserve the spirit of the frame-preserving update. So we want to have this implicit version where you as the user decide when you see the update what you actually want to update, which needs this, I think, frame preservation style. Right, so I think the two are quite different, although both do not preserve frames.
Thank you.
Hi, very cool work. I wanted to ask about how inconvenient the proofs are. So one of the benefits of the original Iris that you can try blindly framing everything, and if it doesn't, and if you have some other research left that you start manipulating. But here I saw that depending on the situation, you might need to combine certain resources first to make it stable and then frame it. And I think that might become inconvenient as the proof gets larger.
Very good question. So for existing Iris things that already basically are stable, like the points 2, you can just continue to frame things. And we actually changed the Iris proof mode a bit such that it can interact with the frame modality. And so when you write, iframe, it will just frame those away automatically. For heap-dependent expression assertions, indeed, there's a bit more work involved. It's kind of pay as you go. If you want to use more heap-dependent expression assertions, you also end up with more frame replications.
Right, thank you.
This is really cool. I just wanted to a remark. So Emmerich Fromhertz, in his PhD thesis in the steel logic, has a notion of heap-dependent expressions that he calls selectors that are included in as part of the separation logic of steel. One thing that he has, his selectors are required to always be self-framing, and there isn't a way to sort of split apart the sort of the permission from the heap-dependent expression, which you seem to have, which is cool. But I just thought I'd mention that.
Yes, thanks for that pointer. And it took us quite a bit to actually get the star in between those two guys.
I also have a question. So it's maybe more of an engineering or organizing question. So you said you redesigned Iris from the ground up. So did you actually manage to merge this into mainline Iris? Did you break all the existing Iris proofs? How much of Daenerys is now on top of Iris? How much is merged? And kind of these practical questions.
We broke all of Iris. No. So far we've developed this as a completely separate fork. At some point, we basically didn't change the weakest precondition of Iris yet, and we changed everything underneath. And then we just ran make to see what happens, and it compiled everything. We're a bit surprised. So I think basically the model is sort of just an add-on on top of every single thing. So where Iris has a U camera, we define on top one that distinguishes stable and unstable elements. And we can turn existing resource algebras into ones with unstable elements by just saying, well, everything is stable and there's nothing unstable. So that part is backwards compatible, and I think we could upstream that. Then one would have to see whether we would want to maintain a separate weakest precondition inside of Iris, outside of Iris, that sort of thing. We also did a couple of experiments to see that when you can replay existing Iris proofs, and because everything is stable there, you just write basically imod intro a bunch of times, and then that's it.
Cool. Okay, so let's continue with the next